Good afternoon, everyone. Today is lecture number 5 of this heat treatment class. And today's topic is basically material mechanical properties. Since we people are basically metallurgists, so our priority is to improve the mechanical properties. Fine. So as we have discussed, that heat treatment is one of the best strategy or best technique to improve the mechanical properties. So today we're going to discuss about different mechanical properties in short. So if you people have remember in your introduction to physical metallurgy class, that the properties, basically the mechanical properties such as ductility, your strength, and toughness, right? Ductility, strength, and toughness, stiffness. These are the properties which can be easily determined with the help of tensile test or tension test, right? So this is a very good image of tensile test and what is happening in the material, right? So you can see this is basically an engineering stress versus engineering strain curve, right? And you are loading the sample. The sample is like this. This is a tensile specimen. You can see this is a basically round specimen or dog. It is basically, yes, round specimen or called bottom head specimen. Kind of cylindrical shape. And this part, you understand, this is your gauge length, if you remember. And this gauge length is having a particular cross-sectional area called as A0 and a particular length of L0. Initial length L0 and cross-sectional area A0, right? So you understand the moment you are loading it in an uniaxial tension. Uniaxial tension means the load will be like this and will be like this in this direction only. Uniaxial, in one axis load will be given, right? So what happens here? Just wait. Yes. So this, when we apply load on this tensile specimen, what happens? This gauge length will start elongating, right, with increasing the load value, and the cross-sectional area will decrease with time, right? But let me discuss about this figure quickly. Otherwise, we can see what happens. Basically, this is the strain axis, this is the stress axis, right? And you understand what is stress and strain. Engineering stress is the instantaneous load divided by initial cross-sectional area of the gauge length before test. And engineering strain is the instantaneous length divided by minus original length divided by original length. Anyways, what happens initially when we apply uniaxial stress on this specimen? It will first, you can see the stress is rising. Slowly it will reach to a point called elastic limit. That is proportional to limit first, where stress is directly proportional to strain. Again, it will rise, and it will reach to a point. From this point, this material will start deforming plastically, right? So that means up to this point, from 0 to this much of stress, there is no permanent deformation is happening. That is called, you can call reversible deformation otherwise, or non-permanent deformation, or you can say elastic deformation simply. But from this point, that means up to this level of stress, the material will start deforming plastically. This point is called onset of plastic deformation, right? Because you can see this point is nothing but your yield point or yield strength point, right? This value will give you yield stress. So from this stress value, the material will deform plastically, right? And finally it reach to a maximum value. That maximum value is nothing but the UTS, ultimate tensile stress or ultimate tensile strength. Then after that, this curve will fall, and finally here the rupture will occur or fracture will occur. Fracture means separation of a single material into two parts or multiple parts, because here it will separate into two parts. And if you remember, from here to here, from this yield strength stress value to this much, there is an increase in the stress. Right? This is due to strain hardening phenomenon, or also called work hardening, or also called dislocation strengthening. Due to generation of lot of dislocation in the material, this stress value is increasing to this much value. And finally, from here at this point, you can see what is happening to this, what is happening to the material. A neck is forming, like your neck in your body. This is a neck formation. Neck formation means what is happening? A localized reduction in cross-sectional area is happening. From this point, a localized reduction in cross-sectional area is happening. But you can see before this point, this is the image. Here there is a uniform elongation. The elongation which is happening here is uniform. If you measure the cross-sectional area, it is fixed, constant. But here what is happening from this point, from this point, there is a non-uniform elongation or non-uniform deformation. And this non-uniform deformation is happening due to formation of a neck. That means if this is the neck, that means in this area the cross-sectional area is less, but here the cross-sectional area is more, right? So where the cross-sectional area is less, obviously that will deform more and more. So finally, and the stress required to deform a less cross-sectional area is less or minimum. That is why the curve is falling down, and finally at a point they will separate into two pieces. This is the fracture point. And this necking, and so from here this is necking, called necking phenomenon. Necking phenomenon, you understand, there is a non-uniform deformation occurs, but there is a uniform deformation before necking, this part. Okay, so basically this is a curve for a ductile material, when the material is ductile. Now, as you know, important mechanical properties often from tensile test: strength, ductility, and toughness, and stiffness also. Stiffness. Stiffness. And another important property which is not obtained from tensile test is hardness and wear resistance. These are also good mechanical properties which should be memorized. Hardness and wear resistance. Okay, so you can see strength. So strength of a material, you understand there are basically three kinds of strength: yield, tensile, and fracture strength. So what is yield strength? Okay, fine. So this point in a stress, engineering stress versus strain curve gives you the yield strength. So you can see that means from this point plastic deformation initiates or start, or there is a transition from elastic to plastic deformation starts. So you can easily define by looking at this stress strain curve that yield strength is nothing but that value or that level of stress from which plastic deformation starts, or there is a transition from elastic to plastic deformation happen, right? And you also can, okay, here it is written that level of stress where onset of plastic deformation occur, that level of stress for which from which where there is a transition from elastic to plastic deformation occur, right? Then what is UTS? UTS, this point, maximum stress point is UTS, right? So you understand it, you can define it easily. That is the maximum level or maximum value of stress which can be obtained from uniaxial tensile test, right? Because it's the maximum value of stress which we can obtain by this uniaxial tensile test. So it can be defined like this simply: the maximum value of stress or maximum level of stress which is obtained from uniaxial tensile test. So this is a UTS. The definition is very simple. Or you can also like define like this: it is the maximum stress which a metal can withstand before failure occurs. It is written also, I think. Let me see. Yes, maximum level of stress which is obtained in uniaxial tensile test, and it is maximum stress a metal can withstand during uniaxial tensile test. Yes, and you can see the slope is 0 here. The slope is 0 in this point. but before that slope is not 0. Okay, fracture strength, this is, you can see, this is the fracture strength, the stress level at which material is separated into two components or many components. That level of stress is called fracture stress. Yeah. If you people remember, can anybody tell me in between this strength or the stresses, which stress is more important in case of designing a material for a application where there is a lot of load is acting, or severe load is acting, or load is acting on the material? So which strength or which is important here? In between this strength, which strength is more important during designing of a material? Before putting the material into application, which strength is more important? Which strength the engineers basically look upon?
Sir, UTS.
UTS. Okay. Any other? Anybody want to speak something? He's saying UTS.
Sir, both yield strength and UTS.
Both yield strength and UTS. What about others?
Sir, yield strength.
Yes, Latmika is right. Exactly, yield strength is very important. Whenever a designing engineer is designing a material for a particular application, in that condition, yield strength is most important. Why? Because you understand this is a yield strength, right? Yield strength means at this level of stress or at this value of stress, plastic deformation starts. So a design engineer never wants that during application the load should be such that, or the stress acting the material is such that plastic deformation will happen. It never wants, right? So to prevent the plastic deformation to happen in a material, the yield strength is the measure criteria. So for a designing engineer, yield strength is the measure criteria to design a material, right? So you have to remember this one. But when you are deforming a material, like you are deforming a like you are deforming a slab or bloom or billet after casting. So in that condition, two things are important: this one and this one, right? Because if you know the yield strength, then you have to apply such a load which will, or such a stress, that stress should be greater than this one, so that plastic deformation happen and there will be change in shape will occur. You can convert your slab into plates or coils and all, right? But it should not be greater than this one, because necking will start, it will lead to failure. So these two strength are important during our plastic deformation, when we are doing rolling, forging, extrusion, right? When we are doing mechanical working on materials. But when we are designing the material, this strength is more important, yield strength, because we don't want our material to deform during application purpose. Do you people want your bridge to be bend or deform while you are riding your car? Do you want that? We never want that, right? Okay, sometimes what happens, okay, let me move it quickly. Sometimes what happens, there is a 0.2% offset method. This is a very interesting method. For example, you have a very ductile material, like in case of pure aluminum. So what happens exactly, when you draw a stress, engineering stress versus engineering strain plot, what happens, the curve will be like this. So if the curve will be like this, you cannot say basically where is the yield point or where is the yield strength of the material, right? Here there is a not clear cut visibility of yield strength. So what you need to do, is you have to do 0.2% offset method. So what is that exactly? This is, you understand, it's a strain axis. So from 0 strain to 0.2% strain, you reach here. Suppose this is the 0.2% strain. 0.2% strain is from 0 to this one. From here, you have to draw a line parallel to the elastic, to the linear portion. This is the linear portion of the curve. So you have to draw a parallel line from here, from 0.2% strain to this line. So it will cut the plot here, right? Where it will cut, that point will give you the yield strength, or that is called 0.2% offset yield strength. I think you probably understood, or few people get confused. In some textbook, if you go through that, they have written 0.002 strain. That means either you take 0.2% or you can take 0.002 strain. That means from this 0% zero strain, from zero strain you go in this direction to 0.002 strain, right? Then you draw a parallel line to this line, right, to this linear line. Where it will cut, that point will give you yield strength. That is called offset method, yield strength. Then okay, fine, now we'll discuss about ductility. So you understand, okay, ductility. See, this image you understand, this is a, already have explained this one. Okay, ductility, we can define ductility like this. It is a measure of ability of a material to deform plastically before fracture, or maximum strain experienced. This is another very good definition. Maximum strain experienced by a material before fracture. So that means what? That means this axis, strain axis, will give you how much ductile your material is. Suppose after reaching at this point, I will draw a projection onto the strain axis. So this is the strain at fracture, or fracture strain, right? I think I have drawn a graph. Okay, this one. Let's look at this one. So after reaching at fracture point, you have to draw a projection onto the strain axis. So this is the strain at fracture, or fracture strain. If the fracture strain will be more and more, that means the material is more ductile. If the fracture strain will be less, suppose fracture happens here, for example. At this point, fracture happens. So if you draw a projection here, so this is less ductile as compared to the this one, right? So that's why the definition is like this: maximum strain experienced by the material before fracture. So this axis will always give you the ductility behavior, and this axis will always give you the strength behavior of the material. And you can see, okay, so how ductility is measured mathematically? Ductility can be measured by two means. By help of your length, by help of your cross sectional area. You can understand, this is your cross sectional area and this is the length, right? And as I told during the test, this gaze length from this black point to this black point increases, but the cross sectional area decreases. So you understand, more is the reduction in cross sectional area before fracture, more is the ductility, right? And if more is the increasing in the length of this gaze length before fracture, more is the ductility, right? So they can be expressed in terms of reduction in cross sectional area. They can be represented in form of increasing in the length, right? So this is called percentage total elongation at fracture. So percentage total elongation at fracture is instantaneous length minus original length divided by original length, right? And reduction in percentage reduction in cross sectional area. This is cross sectional area. Which cross sectional area I'm talking about? Can anyone tell me? Percentage reduction cross sectional area.
The middle parts cross sectional area.
Middle. Don't tell me middle part. What is the name?
Gauge length.
Gaze length here. Gaze length. Very good. Gaze length. From this black point to this black point, this is the gaze length, right? So why you are not talking about this one, or this points, this area, cross section area?
That is for gripping.
This area is for gripping. Very good. But just beside that,
তাহলে কি চেঞ্জেস আসেনি?
what? Sorry?
କିଛି ଚେଞ୍ଜେସ୍ ଆସୁନି ଯେ ଧରାଇବା ପାଇଁ ହେଇଛି.
Changes asu? What it mean by changes?
So that is not undergo any deformation.
Actually, as I told in the initial part, the gaze length portion is having a fixed or constant cross-sectional area before test. If you measure the area, cross-sectional area at any point, they are same. But far away from the cross-sectional area, gauge length, the cross-sectional area may change. It may increase, right? And grip portion, it is maximum. Okay, anyways, so percentage cross-sectional area reduction is, this is initial cross-sectional area minus instantaneous cross-sectional area divided by initial cross-sectional area. So let me tell you a very good part of this. Many people get confused with this formula. That is percentage total elongation and fracture and percentage cross-sectional area reduction. People get confused. Which one will take in numerator and which one will take in denominator. The best way to remember is, you have to remember the thing is what? Always take in the numerator bigger value minus smaller value, right? And in denominator, always take the initial part, right? Again, I'm saying in the numerator, always take bigger value minus smaller value, and in denominator, always take your initial part. As you can see, this one, this is the bigger value and this is a smaller value, and this is the initial value. Similarly, this is bigger value, this is smaller value, and this is the initial value, right? In this way you can remember. Okay, fine. There is another very interesting property, toughness. So toughness can be also obtained from a engineering stress versus engineering strain curve, right? This area under the curve, the area under the whole stress strain curve will give you the toughness value. So more is the area, more is the toughness. Less is the area, less is the toughness, right? So definition is, it is the measure of ability of material to absorb energy up to fracture, right? Or the amount of energy absorbed by the material before fracture, right? And it is measured by sharp impact test. Basically, there is sharp impact test, that is a different test than that of this engineering tensile test, right? But by doing tensile test, you can also see the toughness value, how much tougher your material is. Similarly, another important property is for resilience. Resilience is this one, area under this curve. This is your yield strength or yield point, yield strength, right? So from here, this area is called resilience, measure of ability of material to absorb energy during elastic deformation, right? And this amount of energy get dissipated during unloading, right? When the moment you do unloading, this amount of energy will get dissipated to that moment. So I'm talking about stiffness. Young's stiffness is also called Young's modulus or elastic modulus. This is obtained by taking the slope here. If you take a slope here in the linear portion, if you take a slope, that slope will give you the Young's modulus or elastic modulus, or that is stiffness value. That means suppose your curve is like this, but if I will take another material and your curve will be like this, for example, and it will move like this. So can you tell me which one is having high stiffness? Initial material or this material moving like this?
Initial material.
Obviously initial material. Why? Because this curve is more steeper, right? The slope will be more, right? So this is having high stiffness. So similarly, if you compare between aluminum and steel, steel is having greater slope, right? So it is more stiffer than aluminum. I think you people have understood all these important properties of a material. Okay, you can look at this one, these curves. Okay, fine. Look at this curve, right? This pink color shows a brittle material behavior, and this is the blue curve shows the ductile material behavior. Many times in interview they ask to draw a engineering stress versus engineering strain curve of a brittle material and ductile material. So this is the beautiful image you have, or you can draw by yourself also, which I have drawn here like this. For a ductile material, you can draw like this. So you can see there is a question like this: how you can distinguish a brittle material from a ductile material with the help of a tension test or tensile test? The answer is very simple. you have to look at the fracture strain. See, for a ductile material, the fracture strain is this one, and for a brittle material, the fracture strain is this one, right? So in which case the fracture strain is more and less?
More in ductile,
Ductile
less
more.
brittle material.
Obviously, because I told you this line, this axis will give you, the strain axis will give you ductility behavior, right? Always you have to remember. So that means you have to perform a test first. After performing a test where the material will get fractured or ruptured, you have to draw a projection on the strain axis, and that point will give you fracture strain. So if the fracture strain is below 5%, if the fracture strain is below 5%, then it is a brittle material, right? If the fracture strain is above 5%, it is a ductile material. And
Hello, sir.
yes,
Sir, 5% of what?
5% of what? Sorry, pardon, I don't understand your question. What 5% of what?
Strain 5%.
This axis, just look at this one. This is strain axis. 5% of what? What means 5%
Okay, sir.
strain?
Okay, sir.
If the strain value will be less than 5%, right? And
Okay,
now
sir.
you are, how to get the strain? Just by dropping the projection from the fracture point, like this. Is okay. Anyways, this is clear. Next, there is an interesting point here. Brittle material under tensile and compressive load. So you understand which one is tensile, which one is compressive? Tell me quickly.
First one tensile, second one compressive.
Very good. This is the tensile force acting on a material, and this is the compressive force acting on a material. Just by looking at the direction, you can say which one is tensile, this one is tensile, this one is compression. The question is why the brittle metal have high compression strength than tensile strength. This is the important point about a brittle material. You have to remember. For example, ceramics, glass. Ceramics and glass are brittle materials. They can withstand more compressive load, right? But they cannot withstand a tensile load. Can anybody tell me why? Just looking at this image, can anybody tell me? Suppose this is a ceramic and this is also a ceramic, but this ceramic is now under tensile load and this ceramic is now on compressive load. So why brittle metal have high compression strength and tensile strength? Tell me, just by looking at the image. Carefully look at the image and tell me. It's very simple. You have understood the question, or shall I repeat?
So because it is easy for the crack to propagate through
Yes,
that
yes.
portion,
Propagate in
but
which case? In which
in
case?
case of tensile,
Tensile. Very good. Very good, Sivasis. Excellent answer.
but in case
Yes.
of compressive, it is not that easy.
The image is showing itself. That's why I have drawn arrow marks at the crack points. Just look at this one. This is a brittle material and it is in the tension now. So what happens? There is a already crack is present, right? And the force is tension, for example. So what will happen? The crack opening will be more and more. Now you got the point? The crack opening will be more and more due to tension in the brittle material. And once the crack opening will be more and more, what happens? The crack will propagate easily in the material and fracture will happen, right? But in this case, what is happening? Just opposite. Can you tell me what is happening here? If the force is compressive, just opposite, the crack opening may not take place easily. It will, rather than it will get closed up, basically, right? So tensile load helps in the opening of crack and propagation of crack, but this kind of load is not helping in opening of crack, right? So that's why brittle metal can withstand more compressive load as compared to tensile load. So whenever you have a compressive load acting on a you can use brittle materials, right? The best example I told you, the cast iron. cast iron is comparatively brittle as compared to that of the steels. So they are used in the base of the heavy machines, heavy machinery parts. Bottom part is made of cast iron. They can withstand more compressive load, right? Anyways, and defecting crystals. Do you people remember the different defects in the crystals? Tell me quickly, what are the different defects in the crystals?
For vacancy, interstitial, and dislocation.
Only okay, fine. Vacancy, interstitial, and dislocations. Any other defects we have in our materials? Defects in crystals means crystalline defects. Huh?
Line defects, sir.
Line defects. Okay, what are the example of line defect?
The dislocation, like
Very
bow
good,
dislocation as
dislocations. Very good, very good. Already, I think I have taught you all these things in your IPM class. Just please go through that. I'll not discuss much in details here. Point defect, let me give you a simple example as Rameshwari told. Vacancies, interstitial atoms. Line defect, best example, dislocations. Screw edge. Surface defects, grain boundary. Right?
yes, sir.
Volume defect, if you remember, anybody? Anybody remember any volume defect?
So stocky defect.
You are talking about the Schottky?
Voids,
Yes, sir.
Schottky defect, that is basically happens in the ionic materials, but we are talking about crystalline materials, basically metals and alloys. Schottky defect happens in case of ionic materials like sodium chloride and all. Precipitate can be a precipitate. Inclusions.
sir, void habo.
Void can be, yes, ହେଇପାରିବ. Precipitates, inclusions and all. Okay, anyways, so basically from all these defects, this most important defect is this one, which is sometimes good and sometimes bad. So okay, fine. So okay, can you people tell me defects are always detrimental or deleterious for or crystalline materials, or sometimes good? Or can you tell me about this?
Yes, sir. There is an equilibrium concentration of defect present in a material always.
Yes, that's fine. But my question is, do you people think that defects are always detrimental or deleterious for our materials property? They deteriorates our properties always.
No, sir. Sometimes
No, sir.
it is good.
Sometimes good. How can you justify that?
It will increase the strength of that material due to high
Very good, very
dislocation
good.
density.
Okay, very good. Excellent. So defects, basically crystalline defects. The best example you can give is high dislocation density. Do you people remember the dislocation density formula? Or what is the meaning of dislocation density? These are some examples. Number of dislocation per unit volume, or what? Okay. So now okay. We fine. Now I will discuss about the strategy. This is the most important topic we have, because if you want to do your high studies and suppose you are more interested in physical metallurgy, basically, so this part is very important for that. And maximum time whenever you are dealing with increasing in the strength of the materials, so this topic will be very important, and this is one of the topic in your syllabus we have, that is strategy to increase the strength of the crystalline materials. See, so now I think most of this part I have covered this in IPM subject, but again I will discuss in more details. So basically we have, okay, sir, fine. Basically we have two strategies how we can improve the strength of the material. So basically we have two strategies. The first strategy is what? Make a perfect crystal. That is the first strategy we can have. I think you people remember this part. We just by forming a perfect crystal, we can enhance the strength of the materials. Simply by making a perfect crystal, you mean there will be no defects. We have to make the crystal defect free completely. There will be no grain boundary, there will be no dislocation at all, right? We have to remove all the defects from the crystal, making it a perfect crystal, so we can enhance the strength. If you remember, that is called, what is that strength called? If you do not have any defect, that strength in the material is called, a strength of a single crystal is called,
Whisker.
strength of a single crystal is called theoretical cohesive strength. You have to remember that, right? So theoretical cohesive strength, which is very high, you can see the value G by 2 pi. So what happens? The theoretical cohesive strength is gigapascal. You can understand GPa, capital G, capital P, small a, right? You can understand how strength a single crystal is, or a material with no defects, you can see. But basically it should be a single crystal, right? So theoretical maximum shear strength, which is very high, that is 3 order more than that of experimental data, right? Which is due to dislocation in the materials. But you understand, this removing defect is a very expensive process, and it is very difficult. We cannot remove all the dislocation in our materials, because our materials are, and we cannot remove the grain boundaries, because basically the material which we are dealing with are polycrystalline. They are not single crystals, they're polycrystals. Anyhow grain boundary will be there, that is one of the defect. Anyhow we have dislocation during solidification processing, or during any processing routes, we will get dislocations anyhow, right? We cannot get rid of defects. But now that is why the second strategy has come. Second strategy means, if we cannot remove our defects completely from the materials, what we can do, we can introduce more amount of defects in the materials. Just by introducing more amount of defect in the materials, like introducing more amount of dislocations, introducing more amount of grain boundaries, we can enhance the strength of the materials, right? But we cannot reach to gigapascal, that is different thing. But still we can improve our strength, right? And best example of a single crystal is whisker. So these are the two strategies. Materials we use and see are single crystal or polycrystals. Can anyone tell me quickly?
Polycrystal.
Polycrystals. Polycrystals mean
That contains more than one crystals.
that contain more number of grains. Okay.
Yeah.
And now same thing which I have written. So that means you understand if we have a single crystal which is a perfect crystal which is defect free completely, there is no dislocation, there is no grain boundaries, so it is a completely perfect crystal. The strength, theoretical strength is very high, GPa level, gigapascal. But the moment you are but then the material we are using are basically polycrystalline in nature. They have grain boundaries automatically, they have dislocation in that. So due to presence of these dislocations, due to presence of these grain boundaries, basically due to presence of these dislocations, the crystalline materials become weaker, the strength reduces threefold. Here already I have written everything. You can see dislocation makes the crystal weak because due to motion, propagation of dislocation on the application of load, high temperature and load, sleep or plastic deformation in the crystalline material occurs. You can write. Right? So you understand your crystalline material is weak means dislocation is propagating from one position to another in the slip planes, right? Easily they are moving. That's why it is weaker. It is already written here. Or in other words, due to plastic deformation, lot of dislocation is propagating in slip system. Do you remember what is a slip system? Can you tell me quickly?
Closed pack direction in a closed pack plane.
Yes, the closed pack planes and closed pack directions are the slip system. Slip system is a combination of slip plane and slip direction. Slip plane means in that plane, the atomic density is more, right? Atomic density is more over there. And slip direction means in that particular direction, the atoms are closely packed. In simple way, I can say, right? So that means a very low force or very low amount of load can easily move the dislocation in that area, that plane in that direction, right? Less amount of force will be required. In case of BCC, the body diagonal, you understand. In case of BCC, the body diagonal is your slip direction, right? And in case of FCC, it is the face diagonal, right? And 111 plane in FCC and 110 in direction in FCC, right? And 110 plane in BCC and 111 direction in BCC, right? Here it is written, once the material deforms plastically, it is weak. That's why resistance to plastic deformation can be called as a strength of a material. So in simple way, you can say what is the strength of a material or how you can define a strength of material. If there is more resistance to plastic deformation, that means more resistance to dislocation motion, then it is having good strength, right? Here it is written, yield strength, stress required to move the dislocation. Here it is written, if the dislocation motion is easy in the material, then we call its ductility. And you have to remember, strength and ductility are always inversely proportional. If the strength will increase, ductility will go down, right? Or if the ductility will increase, the strength will go down. Okay, by looking at all these PPTs now, can you people tell me what will be the basis or what will be the principle behind the strengthening of material? By which principles you can strengthen a material? By reading all these things.
Dislocations.
Tell it clearly. Yeah, you're saying something, but tell it confidently.
It's a high dislocation
So
density.
My question is how to strengthen a material. What will be the principle behind that? That's why reading all these things.
Sir, create more dislocations.
Create more dislocations. No, I'm not talking about creating dislocation, or I'm not talking about annihilating dislocations. My question is simple. What is the principle behind the strengthening of a material? Just read all these things. I told you what weakens the materials.
Strain
Why
hardening.
strain hardening? No,
Sir, we have to maintain an optimum level between strength and ductility.
no. That is, you are saying, talking about toughness. The simple way, to increase the strength of the material is to restrict the motion of dislocation. You understood now? By restricting the motion of dislocation, or by impeding the propagation of dislocation, we can increase the strength of the material. That is the principle behind the strengthening, right? The principle of strengthening of a crystalline materials, metals and alloys is, so to increase the strength of a crystalline material, we have to impede or restrict the dislocation, propagation, or motion, or reduce the ability of these linear defects, dislocation through the metal and alloys. You people understood now? You understood, right? Now we'll discuss about the way to restrict or impede the dislocation motion in a polycrystalline materials, right? So in a polycrystalline metal, how to restrict the motion of dislocation, or this is called different mechanism of strengthening or hardening. Hardening and strengthening are both meaning is same. So these are the different mechanism of strengthening in a materials. By using this mechanism individually, or using this mechanism in a couple way, you can increase the strength of a material or hardening of material. First one is the grain refinement. So grain refinement means by refining the grain size, by reducing the grain size. Second one is cold working, by doing cold working on the materials, or that is by doing strain hardening, or by doing dislocation strengthening, right? Or this is also called work hardening, right? So just by doing cold working, that is strain hardening or dislocation strengthening or work hardening, you can increase the strength of the material. Just by doing solid solution strengthening. Solid solution strengthening means by adding solute atoms, alloying elements. Just by adding alloying elements or solute atom. It may be interstitial atom, it may be a substitutional atoms, right? Suppose for example, nickel is added to the iron, it will increase the strength simply by adding carbon into the steel, right? Dispersion strengthening. Dispersion strengthening is intentionally we are adding some foreign oxides, basically some dispersoid we are adding, basically oxides, like titanium oxides and yttrium oxides into the steels. Precipitation strengthening. Precipitation strengthening means by generating some precipitate in the matrix, because we have a matrix and precipitate are the second phases, right? And transformation strengthening. Transformation strengthening. Okay, can anybody remember what exactly transformation strengthening means? How you can increase this?
Martensitic
Very good, very
transformation.
good. By doing martensitic transformation. Any other? Any other transformation?
Benetic.
Very good, Benitic. By converting the initial parent phase to non-equilibrium products, right? Okay, here I have written strengthening mechanism and obstacles to dislocations. So these are the strengthening mechanism we have, and this is the obstacle to dislocation. So in grain size refinement, obstacles are what? The grain boundaries, right? That means more number of grain boundaries, more is the strengthening. Similarly, cold working, strain hardening, work hardening, dislocation strengthening. So here the obstacles to the dislocation is what? More density of dislocation, right? Or dislocation forest. Solid solution strengthening. In case of solid solution strengthening is nothing but here interstitial and substitutional atoms create strain field. The strain field is the obstacle mainly. Around the solute atom in the parent lattice. Precipitation strengthening. This is also same. The strain field around the precipitate. That is misfit, if you remember. Then, then dispersion strengthening, same, by creating, by adding insoluble hard particles like oxide particles. The obstacles is your same strength field around the particles. And transformation strengthening by generating non-equilibrium microstructures, martensite and benite. Okay, I'd like to stop here for today, and we will continue the lecture from this grain size refinement.
ಸರ್ ಟಿಗೆ ಸ್ಲೈಡ್ಸ್ ಕೂಡ ಅವತ್ತದಕ್ಕೆ ಸ್ಕ್ರೀನ್ ಶಾಟ್ ನೀವು
If you have any doubt, you can ask me right now. Okay, I think there is no doubt. You can leave.
ಥ್ಯಾಂಕ್ ಯು ಸರ್